Hello everyone. Tonight, imagine you're holding a map, not a street map, not a map of countries, a map of distances. You point to two faraway places, two galaxies separated by so much space that the number itself feels like it belongs to another language. Light, the fastest messenger we know, takes millions or billions of years to cross that distance. Now imagine drawing a line between those galaxies. The line is long, patiently long. But then, as a thought experiment, you take the map and fold it just a little so that the 2 points come close. And in that folded moment, you poke a tiny hole through the paper, connecting the points directly, a shortcut. That image, two distant regions made neighbors by geometry, is the emotional core of the wormhole idea. Wormholes are not confirmed objects we've seen in telescopes. They are not part of everyday astrophysics, the way stars and black holes are. But wormholes are something else that science values deeply. A place where mathematics, geometry, and physical law meet our imagination and then ask for evidence. So tonight we'll do something calm and careful. We'll talk about what a wormhole is in the language of modern physics. We'll explore where the idea comes from, what kinds of wormholes are discussed in serious scientific work, what it would take for one to exist, why that what it would take is so hard, and why wormholes keep returning in discussions of quantum theory, black holes, and the structure of spacetime. And we'll do it slowly, like walking through a museum after hours. No crowd, no rush, just quiet exhibits of big ideas. Spacetime as geometry, the stage that can bend. To understand wormholes, it helps to adopt one gentle shift in worldview. In Newton's picture, space is a container. Time is a separate universal clock. Gravity is a force pulling masses together. In Einstein's picture, general relativity, space and time merge into spacetime, and gravity is not exactly a force. It is what happens when spacetime is curved. A simple way to say it is, matter and energy tell spacetime how to curve. Curved spacetime tells matter and light how to move. So when we talk about exotic structures like wormholes, we are talking about exotic geometries, ways spacetime might be shaped if the universe allows it. And general relativity, as a set of equations, is remarkably permissive. It doesn't only describe one universe. It describes a family of possible universes, many possible space-time shapes, some of which look familiar, and some of which look like puzzles. Wormholes live in that family. The first wormhole shaped the Einstein-Rosen bridge. Historically, one of the earliest wormhole-like solutions comes from the mathematics of black holes. When you write down the simplest black hole solution in general relativity, the Schwarzschild solution, you find something surprising when you extend the coordinates beyond the region we usually consider. The extended geometry looks like it contains two asymptotically flat regions, two faraway universes, or two faraway regions of one universe connected by a bridge. This is often called the Einstein-Rosen bridge. What it is, in gentle terms. Picture space-time as a landscape. A black hole is a deep gravitational region. In the extended mathematical description, space-time seems to contain a kind of throat, like a narrow passage. But here is the catch, and it matters. The Einstein-Rosen bridge is not traversable. If you try to travel through it, the geometry changes too quickly. The throat pinches off before anything can get through, at least in the idealized classical description. So it's like a bridge that appears in the math like a mirage, real in equation form, but not a usable tunnel for a traveler. Still, it was a clue. If general relativity naturally produces bridge-like structures in its solutions, maybe other solutions could produce bridges that stay open. That question leads us to the more famous category: traversable wormholes. Traversable wormholes, the dream version, carefully defined. When people say wormhole, they usually mean a traversable wormhole, a space-time tunnel you can pass through. In physics terms, a traversable wormhole is a geometry with two mouths, entrances in space-time, a throat connecting them, a path through the throat that can be followed by matter or light, and crucially, the throat remains open long enough for something to cross. That last point is where the universe gets picky, a comforting constraint. Physics loves to close things. In ordinary matter, gravity is attractive. If you have a tunnel-like throat in space-time, the gravitational pull of the surrounding energy tends to make it collapse. So the key technical problem is, what keeps the throat from pinching shut? In the most studied models, the answer is something that sounds unsettling, but has a precise meaning. You need exotic matter. Exotic here does not mean alien goo. It means matter energy with unusual properties, typically involving negative energy density or negative pressure in the right configuration, enough to hold the wormhole open against collapse. This is not a casual requirement. It's the central obstacle. Exotic matter, negative energy without magic. Negative energy density sounds like it should be impossible. On everyday scales, it does seem impossible. But in quantum physics, nature allows some subtleties. The vacuum is not empty. In quantum field theory, what we call empty space is not truly empty. Fields fluctuate. Energy is constrained. But it's not always locally positive in the simplest way our intuition expects. There are known effects where, in a limited region for a limited time, the energy density relative to a baseline can be negative. One famous example is the Casimir effect. Two conducting plates placed very close together can alter the allowed quantum modes between them, producing a measurable force that can be interpreted as arising from a difference in vacuum energy. The important part is not the plates themselves. The important part is the lesson. Quantum fields can produce situations that behave like negative energy in specific setups. But there's a second catch: quantum inequalities. Quantum theory does not let you create unlimited negative energy wherever you want. There are constraints often discussed as quantum inequalities that limit how negative the energy can be, for how long, over what region of space. So even if negative energy is possible in principle, sustaining enough of it in the right geometry to hold open a macroscopic traversable wormhole appears extraordinarily difficult. If wormholes exist, they would likely require conditions that are rare, engineered, or tied to extreme physics we do not yet fully control. In other words, quantum theory cracks open the door just a little, then puts a chain lock on it. What a wormhole would feel like, a traveler's story with physics rules. Let's slow down and imagine a traveler because it helps us understand the constraints. Imagine a small spacecraft approaching the mouth of a wormhole. The mouth looks like a region of space, perhaps a sphere, perhaps distorted by lensing where light paths bend strangely. The traveler has a checklist because this is science, not a fantasy. Tidal forces, the spaghettification problem. Strong gravity gradients can stretch objects. Near black holes, tidal forces can be lethal. A wormhole suitable for travel must have tidal forces small enough that a human-scale traveler wouldn't be torn apart. That generally requires a large throat radius and a geometry designed to keep curvature gentle along the path. So a human-friendly wormhole is not a tiny pinhole. It's more like a wide, smooth tunnel in spacetime. Stability. The tunnel must not collapse. As the spacecraft enters, the wormhole must remain open. If the throat collapses mid-transit, the traveler doesn't just get stuck in traffic. The geometry itself becomes dangerous. The stabilizing exotic energy must be present and arranged to keep the throat open. Causality. No paradoxes, if possible. If the two mouths are in motion relative to each other or in different gravitational potentials, relativistic time dilation can create situations where the wormhole acts like a time machine, allowing closed, time-like curves, at least in naive models. This is where physics starts to glare sternly over its glasses. Many physicists suspect there are mechanisms, perhaps quantum backreaction, that prevent wormholes from becoming time machines in physically realistic settings. Stephen Hawking called this idea chronology protection, the notion that the laws of physics conspire to prevent macroscopic time travel. We do not have a final theorem proving this in all cases, but the suspicion is strong because paradoxes are messy and physics tends to be tidy. So our traveler's story becomes not a free-for-all, but a guided tour with strict rules. And that's a theme tonight. Wormholes are interesting precisely because the rules are so demanding. Wormholes versus black holes. Similar shapes, different personalities. Wormholes and black holes are often blended together in popular imagination, but they are not the same thing. Black hole basics. A black hole is a region where space-time curvature becomes so strong that there is an event horizon, a boundary beyond which signals cannot escape to faraway observers. A standard black hole solution does not give you a safe passage to elsewhere. It gives you a one-way trip inward toward a singularity in the simplest classical model. Wormhole basics. A traversable wormhole, in its cleanest version, has no event horizon blocking travel in both directions. It has a throat supported by exotic energy so that you can go in and come out. Some mathematical wormholes are connected to black hole geometries, some are not. Some are transient, some might be engineered, some might be purely theoretical. If a black hole is a gravitational trap, a traversable wormhole is a carefully braced doorway. One is an expected outcome of stellar collapse. The other is a special geometry requiring special conditions. Nature clearly makes black holes. Whether nature makes traversable wormholes is still unknown. How would we detect a wormhole? evidence that would look wrong in a helpful way. If wormholes exist somewhere in the universe, how would we notice? We can't just point a telescope and see a label that says wormhole here. We'd have to infer its presence from effects on light, matter, and gravitational waves. Gravitational lensing, the signature of warped paths. Massive objects bend light. This is gravitational lensing. A wormhole mouth might produce lensing patterns that differ subtly from those of ordinary matter like stars, black holes, or galaxy clusters. In some models, a wormhole could create unusual ring patterns, multiple images with strange brightness relationships, lensing that suggests negative, mass-like behavior in parts of the geometry. But here's the challenge. Astrophysical environments are complicated. Dust, plasma, intervening objects, and ordinary gravitational structures can mimic a lot of weirdness. So, lensing anomalies would be suggestive, not conclusive. Accretion behavior. How matter falls in. Matter near a black hole forms an accretion disk, heats up, and emits radiation. The presence of an event horizon changes how energy is released and how matter behaves. A wormhole might lack a horizon and could allow matter to pass through. That could alter disk temperature profiles, jet behavior, variability patterns. But again, these are subtle, model-dependent differences. Gravitational waves, ringing after collisions. When black holes merge, they produce gravitational waves with a characteristic ring down, the spacetime vibrations settling into a stable state. Some theoretical work suggests that if the objects were not standard black holes, if they were exotic compact objects, possibly including wormhole-like structures, the ring down might include echoes or deviations from the standard pattern. Searches for such features have been discussed, but as of now, there is no broadly accepted detection of a wormhole signal. So, detection is hard, but not hopeless. The universe has a way of surprising us with data that refuses to fit the simplest story. A quiet mathematical interlude, what the equations actually demand. We can say a few precise things gently without turning this into a classroom. In general relativity, the geometry of spacetime is related to energy and momentum through Einstein's field equations. Traversable wormholes, in many standard constructions, require violations of certain energy conditions, assumptions about energy density being non-negative for all observers. These energy conditions are not laws of nature in the same way conservation of energy is. They are reasonable assumptions that hold for ordinary matter in ordinary circumstances. Quantum fields, however, can violate them in limited ways. So the situation is classical physics with ordinary matter. Traversable wormholes are strongly disfavored. Quantum effects. Loopholes exist, but may be too small or too constrained. This is why wormholes sit right on the border between general relativity and quantum theory, two frameworks that are each extremely successful and yet not fully unified. Wormholes are like a question mark drawn in the seam between them. Wormholes and time travel, the temptation and the trouble. Time travel enters the wormhole discussion for a reason. Relativity makes time flexible in a specific, lawful way. The basic trick, conceptually, not practically. If you have a traversable wormhole with two mouths, and you accelerate one mouth to high speed and bring it back, or place it in a stronger gravitational field for a while. Then, due to time dilation, the clocks at the two mouths can become out of sync. In some idealized scenarios, stepping through the wormhole could then let you emerge at a time earlier than you entered relative to external observers. This is where science fiction gets excited. But physics gets suspicious, because closed time-like curves tend to create paradoxes. And paradoxes usually signal that a model is being pushed beyond its domain of validity. Chronology protection, nature's quiet refusal. Hawking and others suggested that quantum effects might destabilize would-be time machines. The idea is that as soon as a system approaches the conditions needed to create closed time-like curves, quantum fields produce divergences or back reaction that destroys the configuration, closing the door before paradoxes can walk through. We do not have a final, universally accepted proof, but the idea fits a broader theme. Physics often allows strange things in ideal equations, then forbids them when you include the full set of realistic effects. So the calm takeaway is, wormholes raise the question of time travel. But time travel is not a guaranteed feature of physically realistic wormholes if traversable wormholes exist at all. Wormholes and quantum entanglement, a modern twist with a famous slogan. In recent years, wormholes returned to the spotlight through a surprising connection to quantum entanglement. Entanglement is the phenomenon where quantum systems share correlations that cannot be explained by classical, local, hidden variables. It does not allow faster-than-light communication in the usual sense, but it does create deep, non-classical links between separated systems. ER equals EPR, a speculative bridge. There is a bold conjecture, sometimes summarized as AE equals EPR. ER refers to Einstein-Rosen bridges, wormhole-like connections. EPR refers to Einstein-Podolsky-Rosen entanglement. The rough idea is that entangled particles might be connected by a kind of microscopic, non-traversable wormhole geometry, not a tunnel you can fly through, more like a geometric way to represent entanglement relationships. This idea appears in certain contexts in theoretical physics, especially in studies of black holes, quantum gravity, and holography. It is not proven, it is not a settled fact, but it is one of those ideas that might be pointing towards something real about how space-time and quantum information are related. And if that's true, then wormholes might not be rare cosmic objects out in space. They might be part of the bookkeeping of reality, tiny connections that encode how information is shared. This is one reason wormholes stay scientifically alive. Even if macroscopic traversable wormholes are impossible, wormhole-like structures might still be meaningful in quantum gravity. Could wormholes form naturally? Speculation with boundaries. If traversable wormholes require exotic matter, could the universe still make them? There are a few speculative possibilities people discuss. Early universe processes. The early universe involved extreme energies, rapid expansion phases, and quantum fluctuations stretched to cosmic scales. Perhaps exotic topologies formed then, like defects or tunnels in space-time, and some survived. But survival is a serious challenge. The universe evolves. geometries that are not stable tend to disappear. Exotic astrophysical conditions. Could extreme environments near black holes, neutron stars, or during mergers create brief wormhole-like structures? Maybe in some models, but again, stability is the obstacle. A transient wormhole that collapses instantly is not traversable and is hard to observe. Engineered wormholes. This is the most science fiction flavored option. An advanced civilization arranging exotic energy densities to hold open a wormhole. Physics can discuss it in principle, but there are no known practical methods. The energy scales, negative energy requirements, and stability control problems are beyond our technology by an absurd margin. So for now, these are thought experiments useful for exploring laws, not a blueprint for construction. If you fell into one, what would you see? Let's return to the gentle traveler's perspective, because sleep-friendly science benefits from imagery. Imagine you approach a wormhole mouth. From far away, it might look like a normal region of space, but as you get closer, something becomes subtly wrong in a beautiful way. Stars behind it might appear duplicated, bent into arcs, arranged into rings. You fire a probe light, an ordinary signal toward the mouth. It disappears, and then, if the wormhole connects to somewhere else and is traversable, your instruments might even pick up faint evidence of its emergence at the other mouth if you have detectors there. As you cross the threshold, you don't feel a bump, you feel geometry. Inside the throat, distances behave strangely. The path that was long outside becomes short inside. Not because you broke the speed of light, but because the route itself is different. If the wormhole is designed to be gentle, tidal forces are small. The interior is quiet. Your body is not stretched. Your ship is not torn. It feels less like falling and more like gliding along a curve. Then you exit. And the sky outside is not the sky you left. The constellations are different. The background glow might be different. The interstellar medium might have a different density. Perhaps you are in a different galaxy. Perhaps you are in a different era, though that part is far more speculative. This is what makes wormholes feel like doorways rather than rockets. They change the map more than they change the engine. But again, this is the dream version, bounded by enormous physical uncertainty. Common misunderstandings, small corrections that keep the story honest. Wormholes are famous enough that a few myths travel with them like luggage. Let's set down the luggage quietly. A wormhole is just a tunnel through space. Not quite. A wormhole is a feature of space-time geometry. If it connects distant regions, it's not tunneling through some external space. It is a way the internal distances can be arranged. If wormholes exist, faster than light travel is easy. Even if a wormhole creates a shortcut, that does not automatically mean you can send signals faster than light in a way that violates relativity's causal structure. The global geometry matters. Many wormhole solutions that look like shortcuts also come with constraints or instabilities. Wormholes are predicted, so they must exist. Physics predicts many mathematical solutions. Nature chooses which ones are realized. The existence of a solution does not guarantee physical existence. Black holes are wormholes. Standard astrophysical black holes are not traversable wormholes. The Einstein-Rosen bridge is a specific mathematical feature of an extended idealized solution, not a stable portal in the sky. These corrections don't ruin the wonder, they refine it. And refined wonder tends to last longer. Why wormholes matter even if they don't exist. This is one of the calmest truths in science. An idea can be valuable even if the universe never builds it. Wormholes matter because they stress test our theories. They ask, what are the true constraints on space-time geometry? What energy conditions are physically required? How does quantum field theory behave in extreme curved spacetimes? Is information somehow geometric? What prevents time paradoxes, if anything prevents them? In that sense, wormholes are like imaginary numbers were to early algebra, strange at first, then indispensable as a conceptual tool, even when they don't correspond to a simple physical object in everyday life. Wormholes might be impossible as macroscopic tunnels, or they might be possible in a narrow, constrained way, or they might exist only as microscopic structures in quantum gravity, or they might exist only in the mathematics. Any of these outcomes would teach us something important, a slow look at stability. The universe doesn't like balanced pencils. Let's linger on stability, because it's the heart of the issue. A traversable wormhole is like balancing a pencil on its point, except the pencil is made of space-time, the table is quantum fields, and the room is the entire cosmos. Small disturbances matter. Passing matter through the wormhole adds energy and momentum. That can alter curvature. Altered curvature can narrow the throat. Narrowing can increase tidal forces. Increased tidal forces can destroy the traversability. So the wormhole must not only exist, it must be robust. Some theoretical studies explore whether certain configurations can be stabilized with carefully arranged exotic energy, sometimes involving thin shells or specific field distributions. But we should keep the tone honest. At present, we do not have observational evidence that any stable, traversable wormhole exists, and the known requirements make them unlikely under ordinary conditions. The universe is capable of extraordinary things: black holes, neutron stars, gravitational waves, but wormholes ask for extraordinary things of a different kind. Not just extreme density, but the right kind of stress energy. A gentle cosmic perspective, distance, shortcut, and meaning. Now, step back from the equations for a moment. Why do humans love wormholes? Because distance is one of the universe's main themes. We look at the stars and feel instinctively that the universe is too large, that our lifetimes are too short, that speed is too limited, that the map is bigger than the traveler. A wormhole is a response to that feeling, a geometric mercy, and science, even when it is strict, understands the emotional question. It just answers in a different language. Science says we will allow wormholes as a possibility if the laws permit them and evidence supports them. And so far, the evidence is quiet. But the possibility remains like a door drawn on a wall, waiting to see whether the wall is real or whether it's a curtain. What we might learn next, the future of wormhole talk. If wormholes ever move from theory to evidence, it will likely happen through subtle data, not dramatic footage. Possible future paths include better gravitational wave measurements, improving our ability to test the ringdown of compact objects, higher resolution imaging of environments near black holes, looking for deviations from expected shadows and accretion behavior, more precise lensing surveys that might catch rare, odd lens signatures, theoretical progress in quantum gravity, clarifying whether wormholes are natural features of entanglement and space-time emergence. Even if no wormholes are found, these efforts still improve our understanding of black holes, gravity, and the structure of the universe. So the journey isn't wasted. In physics, even a no answer can be a powerful map. A tunnel of thought, not yet a tunnel of space. Now let's return to where we began. The folded map. Two distant points, a long path, a gentle fold, a hole connecting them. That hole is a wormhole in its simplest metaphor, distance reduced by geometry. In the real universe, wormholes are still unconfirmed. Traversable wormholes likely require exotic energy configurations that may be beyond what nature commonly provides. And time travel versions of wormholes run into deep issues with causality and stability. And yet, wormholes remain one of the most elegant questions we can ask space-time. If the universe can curve, can it also connect? If geometry is flexible, what shapes are allowed? If quantum theory and gravity share a deeper structure, could wormholes be the seam? These are not anxious questions. They are the quiet, kind questions that expand the mind without tightening it. So, as you rest, let the idea of a wormhole be what it is tonight. Not a promise of escape, not a guarantee of portals, but a calm reminder that reality is wide enough to contain strange possibilities, and that our best theories, when followed carefully, still lead us to mysteries worth holding gently. The universe doesn't rush. It curves. It waits. It keeps its secrets at a patient distance. And in that patience, you can sleep by sweet dreams.